What's up you guys, it's Peter here, and in this video I want to continue with the information on the SDF or the signed distance field. I want to cover some examples and some use cases where you might want to use the SDF and how you can use it into your systems. Now, if you've missed the previous video, that was more on the theory on how to work and the workings of the SDF, so check that one out if you haven't already. So let's dive into Houdini and have a closer look. So how does it work? The signed distance field is what we're covering, so let's dive outside of the SDF explanation, and I'm going to dive inside of my SDF examples. So let's rewind this just for a moment and talk a bit about it. So I'm going to start simple with a sphere, and then we're going to go to the pig's head and do some operations with it. So first of all, notice that if I were to use a primitive sphere and I do a VDB from polygons, it will try to convert this sphere into polygons for you, and you can kind of see the faceting of the geometry. So I don't particularly like that when I'm turning my polygonal geometry into an SDF. So instead, I can turn this into a polygon myself, right? And just say, give it a high frequency of detail. So if we look at this polygon detail, there's a lot of polygons there. And so when the VDB from polygons takes place, it's going to be much, much nicer. So just a little caveat when using primitive spheres versus polygon spheres. Next up, we can kind of see what can we do with this? The volume VDB from polygons over here, I'm giving it an exterior band. Now I can build this together with you guys, or we can kind of go through it. Now I've already built a file over here that we can kind of dive inside. And so one of the things that we want to do is potentially displace this, this VDB, this SDF, right? So how does that work? Well, notice I've turned on my exterior bands and I've given it here a volume of displace distance and over here another distance. So I've got two displacement operations here, this volume of displace and another displace, which is basically the same thing. So let's step through this and see how this works, right? So over here, if I displace this outwards, and I'm going to displace this one outwards even more, right? We can build ourselves quite a bit of detail, right? So it's kind of like a detailed operation, and this will be the procedural way. So we can dive inside and visualize this, or we can build this from scratch. Maybe I'll build one of them from scratch using an attribute volume VOP. Let's see, a volume VOP. This will be my cheat sheet in case I get lost, but I don't think so. So let's try it. A volume sample over here is the first thing that I want to do. So I'm going to sample from the current position. I'm going to sample using the second input. Now the second input, oops, there is only the first input. So I'm going to sample in a moment the SDF from the first input. And what do we want to sample here, right? Currently it's going to sample primitive number 0. Now we only have one primitive. We only have over here the surface. Now, why would you want to sample other volumes? Well, maybe you have a rest volume, maybe you have a temperature field, maybe you have a velocity field. So the volume sample can do more than just sample the signed distance field. Currently we are dealing with the signed distance field, but notice something else, right? Here it is trying to grab density and output it in density. Now the VDB from polygon operation by default over here creates a surface. Now let's also just copy this along just so that I don't have to deal with this. I'll turn this off and let's give it, I don't know, maybe a range of 10 by 10. So that gives me 10 voxels on the outside and 10 voxels on the inside. So if we look on the inside, you kind of see, remember that fill interior bit, right? So that is going to be useful for the inside as well. Now, for the outside portion, also, whilst we're doing this, probably a good idea to save the scene as I go, because now I am building new stuff. So here, volume VOP, if we dive inside, we can literally just sample the value and just shove that into our density. Now, if we look at this, it won't appear that anything has changed. But what we are going to do is we are going to manipulate the position, the sample position over here. So as it samples it, we're going to manipulate that. Now notice also on my volume bindings over here, currently it's auto bind by name. Now, technically, we are not really shoving that into the density field, right? We're going to see if we need to fix that. Here I've fixed it, bind each to density. So I'm basically forcing everything to be bound by the density. We'll talk about that in a moment. That has to do with the way that this thing is named. So whether it's named surface rather than density. Notice that VDB from polygons over here could potentially output a density field too. That would be a fog volume. This is an SDF. So, but we're going to stick with surface. All right, let's dive back inside. And so what I want to do is I want to manipulate over here the sample position. So if I were to say, go give me a turbulent noise, right? And distort the values, right? And we can say, okay, this could be a 3D noise, and add a little bit of that noise to the sample position. So here, add a little bit of the noise to the sample position and shove it in there. And this is going to immediately warp and displace. But note something, we've got some problems, right? So here there's a huge hole in my SDF. Why is that happening, that hole? Well, we basically displaced it so much that it is outside of our bands. And notice over here, it's kind of like, it can't get more information. So what should we do? Well, if we are going to displace that much, we may need to increase the amount of bands. So if we were to set this to 20, maybe it's enough. It looks like it is enough. And we can indeed see that now this entire region over here is closed and covered, right? So we started off with a clean sphere, and after just displacing once, we already have a fairly detailed operation. Now, the next thing that we can do, just to double check that we absolutely don't have any holes, is convert this VDB into polygons. So using a convert, I can simply convert this over here to polygons. Notice that the ISO value is currently set to 0. Remember what I said, we can have a region, an ISO contour, a region where all the values are the same. Well, this over here will give you a surface where all the values are the same, where all the values are 0 or 0.1, right, or negative 0.1. And so this allows me to slice into my SDF, or if we slice too far out, we're going to, basically be on the outside and it won't work anymore. So 0 is a good starting point. So that basically gives me kind of, polygonal representation of my SDF. Now, the next thing that I want to do is, this is a distortion, right? So it's displacing both inwards as well as outwards. What if I only want to displace outwards or only want to displace inwards, right? So kind of like a displacement along the normal of the volume. Now, what is the normal of the volume? Well, that's where we can use the gradient of the SDF again. So let's go and have a look at that gradient. So in order to make that, we start typing volume gradient, and I'm going to bring in the gradient. Now we're going to modify this a little bit, so whereby we're still sampling from the same position. We're still going to grab it based off of the volume. This is going to give me that gradient vector, and I'm going to normalize, right? That's the first step, right? Normalize that gradient. Now notice this is computing every time, that's why it's a little bit slow. So I'm going to visualize just my spheres whilst I'm working. Okay, so eventually I still will need to do the volume sample from file, but what I'm going to change is the way that this distortion is happening, right? So I'm going to say, okay, we have my gradient vector over here. And if we think about this, right, if this nice and clean surface is going to be undulating and it's going to sort of warp to the outside, that means that a voxel that is over here sitting on the outside will need to sample, let's say, the 0 ISO contour. So the voxel on the outside needs to sample the 0 ISO contour. In the previous video, I showed you that the gradient is pointing from the outside, or from rather a positive value to an even higher value. So from a low value to a high value. It could be from a negative value on the inside to a high value on the outside. But basically it's pointing from low to high. So in our case, where we're using the SDF, it is going to be pointing outwards, right? Now, because we're doing a volume sample operation, it's a little bit different from, let's say, a polygonal displacement where we displace the polygon by some normal. We're instead going to do a lookup. So that means from the outside vector, I actually need to look up the surface on the inside. So that means the gradient that I want to use, instead of pointing it outwards, I'm going to flip it around and make it sample the other way. So we're going to also need to negate this. And this is an important step. If we do not do this, right, then our displacement won't work properly. So we're going to negate this. So great. Next, I don't necessarily want to displace distort instead. So we can break this. Instead, I'm going to turn this back to a 1D noise, and I'm going to use over here this vector as my starting point. So we can say multiply this vector by the noise. So instead, right, this is going to be the displacement along a vector. So instead of just displacing any kind of random 3-dimensional vector, we're going to displace along the gradient vector. And we're going to use that one instead, right, to over here add to our lookup sample position. So let's open this up a little bit, right, just so we can kind of see. Here's my volume gradient. It's normalized, it's negated, right? Then we're going to add a mask. This is a noise mask. We can add any other kind of mask, and maybe later on we do that. We can add any other mask to that, but here's my turbulent noise. Currently, it is of type alligator noise. Now, alligator noise is in the positive domain, sort of 0 to 0.5 positive domain. If we were to say sparse convolution noise, it might go between negative 1.7 to positive 1.7-ish. So we can also put an absolute value onto this just to enforce that this mask, right, is only ever going to be in the positive domain. Later on, we might change this so that it goes into the negative domain, and you'll see what that does to the result. So the output over here then is going to get added. And one last thing that might still be useful to have is maybe a global displacement, right? So if we say over here, a parameter that allows me to create a global displacement value. So here, let's say displacement, and let's set the default to something small like 0.1. Okay, let's have a look at what this is doing. Right, so it's actually working, but it's very subtle, right? So basically my displacement over here, as we kind of crank this up, we can kind of sort of start seeing, all right, it is displacing. Now again, if I displace too much, right, beyond the bounds of my object, we're going to hit those limits. So this is where a bit of automation comes into play. So what if I grab this displacement operation over here? This is in world space distance, right? So it's going to displace by 0.5, right? So if we look at this, right, it's displacing from a value of here all the way to 0.5. So this is -2, -1. So it would displace quite a lot. So what I can do is literally link these two parameters, my displacement value over here, copy this and displace it. Instead of using exterior banded voxels, I'm going to use it as a world space. So let's turn this to world space, and we can see currently 20 voxels represents 0.4 in world space, and I'm trying to displace by 0.5, so that's risky, right? We run the risk that we somewhere displace outside of our voxel range. So let's link, copy this parameter over here, this displacement, and then let's link that to our exterior band, paste relative reference. And then if you wanted to, you could do times something small like 1.01 so that it is ever so slightly a little bit bigger than whatever my displacement value is, right? So now no matter what I'm doing for displacing, right, our values will always be covered. So if we convert this, you can basically see that, you know, the displacement is properly working and we don't have any holes. So that's nice. This is a first layer of displacement. Now it would be nice to layer both layers of displacement. So this would be a first layer, and so we can do that again. Now, the other thing that would be nice to have is basically have access to all of these frequencies, amplitude, roughness, and all those settings. So under View Vex Options, I'm going to quickly create the input parameters, and that is going to create all of these for me so that on the outside I have control now over saying, okay, what type of noise do you want? Do you want sparse convolution noise, right? Looks a bit different now. Or do you want Perlin noise? You know, again, maybe this is a bit too much displacement. Kind of wondering, probably the range is off. Original Perlin noise might work better. Okay, but so the base of the system is in place. Let's stick with alligator noise, and now we can kind of specify, for instance, if we don't want roughness, we're going to have like very soft undulation. And the cool thing is we could potentially run this again. So let's do another volume VOP, so the same thing over here, right? And remember, we're actually not dealing with polygons, but we're dealing with voxels. So this is our voxel data over here, and I can basically do it again, right? So over here, we're doing it again, but this time I'm going to say only displays by 0.1, but let's increase the frequency. So let's set the frequency much higher. Let's say 4 by 4 by 4. So now we're going to have, like, you know, big undulations and smaller undulations together. And so lastly, we can kind of start to make sure that also this second volume VOP is taken into account. So here, the exterior bands, you can kind of see that first one. And maybe we can say plus the second one. So what is our second one going to look like? It's going to be volume VOP 2 displacement. And because we are adding, we need to put this in brackets as well. and then scale all of that up. So that is going to simply allow for these bands to simply expand a little bit more. And that's going to cover the scenario of this displacement over here. Let's make it round numbers 0.6 and this displacement of 0.1, right? But notice that the frequencies are different. That's what's going on here. So if we look at that, we get some nice kind of, undulating noisy spheres. Okay, so cool. The next thing to do is, what if we have this, right? And if you want to really crank up the detail, you can kind of set your voxel size lower and lower until eventually, it takes a little bit more time to compute because this is doing own voxels now. But you're going to get all of this high frequency, small scale detail. So this is one way to create really beautiful high resolution detail. So if we look at this now, it's getting quite detailed. Let's turn off the wireframe for a second and just look at this, right? So you get quite nice details onto it. You could potentially bake this down onto a poly reduced version, right? Using some of the Side Effects Labs tools. The Simple Baker is quite nice for that. Turn this into normal maps and so on, make really beautiful volumetric rocks and create high resolution detail and bake all of that down in lower res. So that's one way for modeling. Now, the next thing that we can do with this is, what if we were to do this inside of a solver? So we're doing a displacement on a displacement on a displacement. By the way, you can do this on a polygon surface too, but the problem is, as soon as the polygon surface starts to intersect with each other, you're going to start losing detail and it's not going to look good. Whereas this, because we're dealing with volumes, right? If we do a displacement and another displacement on top inside of a sopsolver, right? It will keep doing it. So the key thing is, right, same thing here, exact same, right? So we basically have our volume gradient, normalize it, negate it, have our turbulent noise, an absolute value of that, so we don't go negative here. By the way, what would happen if we make this go negative, right? If we didn't do that. So, well, we're going to, instead of displace outwards, we're going to be displacing inwards. So if we can either do it here with the displacement value as well. We could set the displacement value to a negative, right? So instead of displacing outwards, we can start displacing inwards. So here, if we look at this, right? Now we gotta be a little careful because I have linked that up to my bands over here. So we're going to go to an exterior band of 0. So maybe let's break that just for a second so that I can display here. Maybe a value of 10 on the outside, so this still works. And let's see, as we kind of go negative, right, we can basically erode inwards into our volume and basically erode our geometry away, which is pretty cool as well, right? I mean, that's fun for doing acidity and other kinds of effects like that. So if we look at our geometry here, right, so we're basically displacing either outwards or we're displacing inwards and eroding away. Yeah, so that'll be fun to do inside of a solver now, so where this thing automatically happens over time so that it updates. So I've built a little example here on the other side, right? So same deal, I've got 6 voxels on the outside and 6 voxels on the inside. So the bands are kind of rough. The geometry is not as detailed. We're dealing with sort of 60 by 60 by 60. So, a little bit of detail, but not too much. So next, let's dive inside of our solver and let's maybe display how this is going to look, right? So the key thing here is, notice that, right, as this thing is sort of expanding outwards, it is updating the voxels, right? And it's kind of, displacing outwards and outwards. And it's quite nice because you can get that kind of pyroclastic, volumetric expansion going. So that's quite fun. So once it's simulated, now we're up to, let's see, 100 by 120 voxels. So we can kind of just play it back and we're going to get quite a cool expansion. And this is all by manipulating that SDF. So let's dive inside and have a quick look. How does that work? Now, at the heart of it, we have that volume displace again. So this is your little worker engine, right? This is your node that is doing the same thing again, but this time inside of a sopsolver. The volume gradient, normalize, negate. Here's my turbulent noise. We could potentially animate any of these parameters, right, of the turbulent noise. Here's my absolute, and then displace outwards. Now, if I were to flip the displacement to negative, it's going to erode away this sphere. So that could be a fun one to maybe play with eventually. We'll try that out too. And then ultimately that is all added together and used for our sampling of our volume sample from file, and then that is fed into the density, which is not really density, but we're binding it to density. Now next, in order for this to expand properly, the active region needs to be expanded. So that means that over here I want to capture more voxels as this thing is growing. So how do you do that, right? Well, we're going to use the VDB activate node to do that. And notice that you have different options. It's a modular kind of tool: position, voxel, expand, reference, and deactivate. I'm going to make use of reference and say activate using VDBs. That means it is going to use over here the second input of this node, and it's going to use whatever activation that we've done here. So what we can do here is use our incoming geometry, convert this temporarily to a bunch of polygons, right? And then simply do a VDB from polygons again, right? Using the same kind of inner and outer limits. So that means that that limit, this is a bit of an expensive way of doing it, but you know, it does work. So this has now converted it back into VDB. And so if we look at the after the displacement, you can kind of sort of see that these bands have updated, right? There's a little bit more detail over here on the outside, and that will happen every time this node cooks. Every sub-step, every step of the solve, it will basically convert it back to polygons and back to VDBs. Now, the reason why I do it this way, rather than simply say, we could have just used a VDB activate, right? And say, well, I could kind of try to sort of expand it by certain voxels every single frame, right? But these voxels will keep expanding and becomes huge, right? And our object needs to be adaptive. So that means it needs to be adaptive against the shell. So we can have it expand outwards, or we can have it shrink inwards. So it'll work both for expansion as well as for shrinking. So let's dive inside of this now, and let's just turn the reference activate using VDB on. And then lastly, VDB Renormalize Sdf. All right, so what does that do? That basically tries to make sure that after we've expanded the values, right, that the value over here is still 0 and that the distance value is still sort of correct to the surface. Because as we kind of just, if we expand and activate more voxels, there's no guarantee that these voxels actually have the correct distance value to that surface. So VDB Renormalize Sdf will try to make sure that over here the values in the voxels are recomputed correctly. Okay, let's output this and let's watch it play. So again, we'll see it expand. Right, so this is fun, and we can convert this at any given moment to a polygonal object. Right, so here, so now we can render this as a polygonal version of this, and it expands. So it's quite a fun thing to do. The other thing is, if you're doing this, you can control this, right? You can say, where do you want this to grow? Currently, it's growing in all directions. But if you're smart about it in a certain way, you can say, actually, I only want it to grow in a certain pattern based off of, I don't know, some curves or another SDF, so that we can kind of say, you know what, you're only allowed to grow inside of another SDF. So it's kind of like using one growth system to grow inside of another mask, right? So how would that work? Well, basically, we could make ourselves a little, let's say we can use this and then grow inside of the pig's head, for instance, right? So if we make a pig's head here, maybe let's scale this up a little bit so it's a bit bigger. We're going to turn that into an SDF, and we're going to limit the growth. It's literally just another mask, just like our other mask was also a mask. Let's see, I'll translate this up a little bit. Here, let's move this out so that my sphere sort of lines up here at the bottom. That's good. We're going to grow inside of this object, right? So let's do a VDB from polygons. There's my sort of representation. We can shove this into our other input. And all that I want to do is here, volume displace. We're going to bring that second input, right? And I'm going to use this as my mask. So what I want to do is I want to specify that you are only allowed to grow inside of that volume. So instead, right, there's also going to be a volume sample from file here, but remember, it is going to be now the second input. So this up input 2 represents the pig's head. Up input 1 represents my own geo. Okay, so let's go grab this one. The sample position, that will just be the voxels that we already have, the position of the active growing voxels. And this is going to return a positive value or a negative value based off of where we are inside of this. So if we say, we can use an if statement, for instance, and say, if you are inside of the volume, so that basically means if your SDF value is negative, you're allowed to grow. If, on the other hand, the value is positive, you're not allowed to grow. So literally, we can just do either a two-way switch or a compare or something like that. So a little comparison here, let's use a compare, and let's say if this is less than or equal to 0, right? So if this is less than or equal to 0, then we are going to allow you to grow. So if this is true, this is going to be 0 or 1. We can literally just multiply that by the displacement amount. So notice that ultimately these are masked. This is a mask, and the displacement amount is a floating mask. This is a random mask. This is also a mask. So we can just simply shove that in there as well, and now it is only going to grow if this is positive. So when is it positive? If it is less than or equal to 0. Yeah. Cool. So let's have a look at this, and let's see if this is working. So we started at least out with a portion of it whereby you know, it's already sort of over here, right? So that's our intersection. Ideally, we put it both of them inside of it, but it'll work regardless. So now if we kind of, you know, let this grow, it is growing inside of where the pig's head is. Now this over here started on the outside, so maybe we should have made that as you know, put the sphere really inside of the pig's head's SDF, so that that doesn't look so weird. Right? Maybe we can do that. We can temporary, or we can move the pig's head, you know, just so that maybe over here it covers the entire sphere. Let's do that instead. That'll work too. Now let's just reset the simulation. So now it'll grow out and it'll basically form that pig's head. All right, so it's cooking 26, 30, and so on. So this does take a while because it's a volumetric operation. It is doing that displacement. It is updating the bounds of the geometry as it is growing. So it's sort of a, you know, like a sparse volume that is adaptively modifying and resizing the active region, right? And so as we kind of play this back, we can kind of see up there it goes. It has reached over here the edge of the pig's head. And so if we let it grow a little bit more, you kind of sort of see it update until eventually it forms and grows inside of that entire pig's head. So this is quite fun to sort of, you know, grow inside of an object, or also erode objects away. So we could do the opposite, where we start with a pig's head and basically erode away and make holes into it, kind of like acidic effects, or, you know, holes in cheese or things like that. So fun to sort of use this VDB inside of a solver. That's really where a lot of the strength comes from. So if we can kind of sort of now see it, it's kind of growing, it's kind of forming until eventually it forms that pig's head. Now, if we don't care about that, we can also just erode away, right? Instead of eroding outwards, we're going to set the displacement to inwards. So if we go back to our sphere over here and set this to negative 0.1, right? Then that vector is going to push inwards instead of outwards. So here now, if we sort of say, okay, erode this away, we can kind of sort of see it is just eating away all of that volume. So this is also a fun application till nothing remains and then it's gone, right? So let's play this back again. And there it goes, right? So it's quite a fun way to melt objects or erode holes into them in certain areas. So yeah, fun stuff. Okay, I've got one more example, but I'll do that in the next video. Thank you. See you in the next one. If you like it, like and subscribe. Thank you.